Hi everyone. So I'm going to be presenting on DisplayPort MST. So first off, who am I? I'm a software engineer at Red Hat. I primarily work on graphics drivers, but have an experience in quite a few areas. And I'm also one of the few MST experts in the community. Mostly because of just how much time I've had to spend fixing bugs with it. So what is DisplayPort MST? Now we already went through a bit of this in Wayne's presentation, so hopefully it's not too redundant. But basically, it's a protocol for DisplayPort that allows for daisy chaining multiple displays in a single link. It's very common in laptop docks, USB-C docks, and even some monitors have the ability to daisy chain one another using DisplayPort MST. We've been supporting it since DisplayPort 1.2. I actually fixed since 1.2a, technically. And it's currently supported in AMD GPU, Nouveau, and i9-15. So why do a presentation on this? There's been a lot of reorganization of the DisplayPort MST code recently. We rely a lot more heavily on the atomic state now, which makes it a lot easier for drivers to be able to actually make decisions related to bandwidth management without having to deal with all of the annoying locking that we used to have to deal with before. Most of this was because we introduced MST support before Atomic had been introduced into the kernel. So originally we had to keep code working for both paths. This also just generally make people aware of the helpers that we have for this. And also because of the fact that DP MST can be pretty rude. It's probably one of the top causes of display issues that I run into in general. So how does it work? So devices which provide ports on the topology are known as branches, and the actual connectors on those are known as ports, of course. Ports on the same branch share bandwidth. So that's what I'm kind of talking about here with the little red lines there. Essentially, we have something in the protocol known as a time slot. Or a time unit. And what that basically is you're taking the amount of available bandwidth and you're splitting it into chunks in order to assign to each different stream that you want to have. We usually refer to streams as virtual channels, or VC for short. And you can have up to 63 or 64 time slots depending on the encoding you're using. 64 for newer DisplayPort 1.2. And 63 for everything else. And then the actual PBN, which is the payload bandwidth number, this is basically a representation of how much bandwidth you're using with DisplayPort. That is generally rounded up to the closest value in time units. So topologies can have multiple nested branches. This means, like, if you're imagining plugging like multiple hubs into each other, that's actually a thing that is supported. But time units are only for the top branch, which is what the red part was indicating before, which means in order to deal with this, we also have to take into consideration the bandwidth limits that come down lower in the topology. For here, for instance, you can see from the source here, we've got it connected to an MST branch. And on that port, it's got an 8.1 gigabit connection. On branch 2, though, it's only got a 5.4 gigabit connection, which means that while the sink is capable of 8.1 gigabytes or gigabits, it's limited to 5.4 gigabits. The way we determine this is each port has its own maximum PBM that is advertised based on the current link rate that it's trained at. So when we're actually doing mode sets, we have to ensure that not only are we giving enough time units in order to a stream, but we have to make sure that down that entire path, we're not running over that max PBN. So payload allocations, I covered this because it's a little wonky with DisplayPort. Basically, payload allocations are in a table like that, and they're always contiguous. There's no holes. So if, for instance, I were to have 3 monitors going, we'll just say they use 5 time units, and I was to turn one off, then the source, or then the sink will automatically, or sorry, the MST branch will automatically shift all of the payloads over to the left side. This is something that the driver actually has to keep track of. We don't get any notifications about this, but it's generally pretty easy. And we're also, that's the most important thing, we're always expected not to have to read back to payload table. There might be exceptions for if we were to handle specific errors where we might want to resynchronize with whatever the current bandwidth allocations are, but for the most part, we're expected to keep track of this ourselves. So basic communication happens via something called sideband communications. If you've worked with DisplayPort before, you're probably used to DP where you basically have a set of registers that you write to in order to configure things. Sideband communications are a bit more action-oriented. Instead of having a set of registers, it's a lot like I2C over aux, where you just have a small number of registers that you use to write your sideband messages. And then the actual hub that you're talking to will handle doing all the lower level DP accesses in order to send that down the chain. Messages can be broadcast or targeted at a specific RAD. Broadcasts meaning that it goes down the entire topology, or RAD meaning you're saying, I want to point at this point in the topology specifically, in which case any messages you send will go one by one down each one and get forwarded until you finally get to the actual target of the message. And there is the ability to do all these DP accesses, because there are a couple of situations where you do need to do that. So commands are actually provided for doing that, but in general, if you don't need to do that, it's recommended not to. As well, for communication that comes to us, like hot plugs and HTTP notifications, those are also done via sideband messages, and we have a set of interrupts known as the ESI, and these basically, you use the ESI in order to clear interrupts, and the actual interrupts are sent via short hot plug detection, IRQs. So now into the troubleshooting, because honestly, this is probably the most important part of this. Because it's a large topology, every single thing down that topology is basically a full DisplayPort device in some way. This means they all have to do their own management of resources, which means there's a lot of places that things can go wrong in that line. And there's a number of reasons that can happen. For instance, the MST spec has been implemented incorrectly many times on a lot of hubs, somewhat understandably, because there have been certain parts of functionality in DisplayPort that are rather complicated and difficult to get right. For instance, there used to be the ability to send interleaved messages, which would basically mean you could queue up two messages at once and they would still be sent out at the same time. This is something we actually had to remove from our MST helpers entirely, because as it turns out, no one ever really implemented it correctly, but they got close, and this is where things start not breaking cleanly. That was a fun one to figure out, because what would happen is it would seem like it was working from the start and all messages would be going through, but then you would get random garbage interrupts. Like you would look at the ESI, see you've gotten an interrupt because you're supposed to get a message, but then there's nothing actually there. And as it turns out, we just had to stop doing interleaved messages entirely because it just wasn't handled correctly on most devices. And then the other thing too is sometimes things don't even break. Sometimes they just take a lot longer than they should. Now the main reason for that tends to be, hold on, let's see if I actually mentioned this in the next one. Okay, no, I don't. So the main reason that can happen is occasionally things may take longer than they're expected to, or something may have failed down the line that the hub is somehow able to just recover from. For instance, when I was doing some debugging, I noticed that with certain hubs, if you send out acts for only once, acts being basically a thing that we send out to synchronize a new payload allocation. If you send them more than once for every single payload, actually as Wayne pointed out at one point, things tend to work. If you don't, what tends to happen is something will fail down the line and you'll see a mode set that maybe takes like 2 seconds to complete, which doesn't sound like a lot of time, but for turning on a monitor, that's actually pretty slow. But even as problematic as MST hubs are, a lot of times we're still kind of the culprit for most of the problems. And one of the big reasons is, first off, like the spec. The specification is, I mean, like all specifications, it's difficult to read. There's a lot of places where you can misunderstand something, and we've done this many times on our side. And as I mentioned before, a lot of device manufacturers have also done this. That's why I always say if you're trying to troubleshoot something with DisplayPort, sometimes literally just rereading the spec a bunch of times will actually end up just pointing out what's wrong. Because you'll finally notice some single line that says something that you missed, and you're like, oh, that's why it does that. And then also the cables. I wouldn't normally mention something like this, but oh my God, it is like, if you're working with USB-C, this isn't really much of an issue, but with full-size DisplayPort, it might be. I haven't run into it, but I know with full-size DisplayPort, the amount of breakage that can happen with the cables is just silly sometimes. Like, I had one incident where I was trying to debug link training issues on the display, and what ended up happening was I was like, okay, maybe this cable's bad. I should try another cable. Doesn't work. A week later, I finally give up. I'm like, I'm gonna try another cable. I know I did this before and it didn't work, and then it worked. And that's why I always say keep like switching cables as much as you can, because it's really surprising how subtle the breakages can be with those. And timeouts. So I had mentioned this before, you know, non-fatal error can occur somewhere down the topology. There's also other things that have resulted in timeouts in the past. For instance, a lot of parts of MST are expected to be handled completely asynchronously. For instance, if you're allocating payloads, you have to be allocating them at the exact same time that you're handling hot plug interrupts, because otherwise something may end up hanging. For instance, you might be trying to send a message, but you can't send the message because you haven't handled an interrupt that's coming in, which means the message times out, which means everything else breaks. And then there's also just delay from having too many nested branch devices, I've noticed. Sometimes, because I've had to do some very silly setups in order to like fully test out hot plugging, because as AMD has pointed out many times, we've had occasional issues where sometimes you will unplug something, and if it's lower down in the topology, the payload actually won't be released because of a bug in the code. But like in doing that, I've noticed that it's very surprising how large the delay can start to get when you start to have like 2 or 3 hubs connected to each other. We actually have a couple of code paths that we've had to add some very large delays to work around this fact. For instance, I think like the payload allocation synchronization we have, we give up to like 3 seconds, which again is very long for turning on a monitor. So the current state of affairs, DRM has a set of MST-related helpers for handling most of the hard stuff, including topology probing, sideband messaging, bandwidth limitations, etc. There's still a lot of features that are missing though. For instance, DSC support. We do have some helpers written, but ideally what we really want to do is we want to have a helper that can handle doing the actual determination of figuring out when we need DSC and when we can turn it off. You actually saw this yesterday with Wayne's presentation where he was plugging in monitors and unplugging them. What was happening is it was literally going through saying, okay, I have this much bandwidth available. Am I able to fit the streams in without compression? No. Okay, so I have to turn on compression. And basically what we want to do is we want to have like a whole set of helpers just for doing that for drivers. So most of the code can probably be taken from AMD for this, luckily, and a lot of it isn't too bad. I've gone through most of it, and a lot of it seems pretty sensible. There's also some other nice things we'd like to have, like fallback retraining, for instance, like retraining at a lower link rate if there is some sort of issue that prevents us from going at a higher link rate and still being able to reset up the same display setup if it fits in the new bandwidth limitations. We also would love to get more comprehensive error handling. This part is surprisingly not as important as you'd think, but it is definitely something that would be super useful. Most of the time, errors would come from something coming out of sync, maybe something being unplugged when it wasn't expected. I don't typically run into them that often, though, which is why I said they're surprisingly unimportant. But it would be nice to actually have that. We also need testing, which Wayne is also working on from AMD. And ideally, we would also like to get actual hardware testing, like from the Chameleon, because then we could actually emulate all of these problematic hubs and actually see if we're handling all of the behavior correctly, along with really stress testing, things like synchronization of the payload table and that sort of thing. We could write unit tests, though. I'm sure we can do that. Anyway, that's pretty much it. Thanks for Wayne Lin for their work on DSC support, bug fixing, and helping out with reviewing that work. And also Vesa for being incredibly cool and helpful. We didn't have access to a lot of the specifications for a while, so we had to do a lot of guesswork. But after working with Vesa a couple of years ago, we were finally able to set something up where X.Org members now have access to specifications. So everyone, please say thanks, Vesa. And say thanks, Bill. There we go. All right, and that's pretty much it. Anyone have any questions?
I think USB-C cables are always good. Just as anything with USB-C, as long as you don't take back too hard, it's great.
Yeah, definitely. Oh yes, what Alyssa said was USB-C cables are great as long as you don't think about them too much. Yeah, they can definitely break as well, but I at least haven't run into the silly issues I have with full-size DisplayPort with them.
It's just a general, comment or regarding DisplayPort is, you mentioned about the kind of all these ambiguities of how it behaves, right? I'll say that when you start dealing with something like DisplayPort, you're really getting into the territory of battling hardware. And so that's that's the mentality you're going to have people dealing with problems and stuff. Listening to the things you mentioned, it's really kind of like, if you kind of have a more idealized software type of mentality, it's what you're going to get hurt. And so you're going to have to deal with harder people. And just for reference, when you deal with DP, I can DisplayPort, it's really kind of like PCI Express. It's probably, there was a lot of influence of PCI Express when they did DisplayPort. So, as a result, like, if anybody has read the PCIe spec, it's a real nightmare. I mean, it's like 900 pages. They sort of wrote it in a way that there's a lot of things that are not, they should be in there, be more specific how you're supposed to implement it, but they don't want to do it. And that's kind of one of the bad habits of hardware people. So, in the future, if you ever deal with these kinds of this kind of hardware kind of centric kind of type of technology, just keep that in mind that hardware people are pretty bad at specifying certain behavior for whatever reason. DP has a lot of influence with PCI, bad influence with PCIe, and that's probably why you've had so much issues. That's just my personal take. I don't have any experience with DP, but I know a little bit of PCIe. So that's why.
Yeah. Yeah. So I think the reality of the situation too is it's not even just like a DisplayPort thing or even like a fault of how it's designed. I think the reality is it's just hard to write specs. Like, as someone who's written specifications, it's very difficult to make sure you're actually going through every single possible thing that could happen. And most times people end up missing something. So I think it's just kind of how it works. And the other thing too is some of the peculiarities, from what I understand, are pretty much because they're trying to make something that will both work on computers, but also can be implemented cheaply enough into actual like branch devices and that sort of thing. So a lot of things that might seem like they're a little silly are probably just done to make those implementations a lot simpler.
I just came on one, not a common question. Did you use the protocol analyzer when you, like tested the software? Like, they were good at-
Um,
You should have.
oh,
You should
yeah.
have engineering to some extent, like validation, target validation, you need to really, get help from those type or hire those type of people for this. That's why, to some extent, like Intel, AMD, or NVIDIA have a lot of advantage in some ways because those guys have access to those extensive like hardware.
Yes.
Program.
So the question was whether or not I used protocol analyzers. Unfortunately, no. The problem is a lot of that stuff for DisplayPort gets really expensive, like absurdly expensive too. But oh no, that's the thing. Even leasing it is expensive. But I mean, we're still. The thing is too, we have things like the Chameleon, where for very specific things we can sometimes use that as a protocol analyzer. But for the most part, a lot of it you can get really far without a protocol analyzer actually, especially too because there's a lot of other ways to figure out if you're getting the right input or getting the right output. But yeah. Any more questions?
This is a question regarding some chips which are both PD and ARC mode, like FSUSD and some sort of chips which are virtual. Look like the current Linux is not supporting those chips with respect to ARC mode DP. Do you have any plan for supporting those?
So I just want to make sure I heard the question right. The question was whether or not we have plans for supporting like USB-C adapters and that sort of thing. Okay.
So, like, for USBPD, right, the framework is moving more and more to URM, right? So, like, what's the PD versus like PD negotiation along with the display stuff? Right now, most devices GCC has off. Linux machines dead.
Yeah, so a lot of time. Oh, do we have to? Yeah. So basically, the question was, what's the plan for handling PD power delivery with DisplayPort? Seeing as now, we have things like USB-C where a device might need to be powered by the actual receptacle. So the good news about that is for the most part, we don't really care about that, mainly because the way it's set up with USB-C is DisplayPort's almost like an entirely separate thing to the point where the way you're dealing with it is barely different between USB-C and full-size DisplayPort. I think the only real difference I can think of off the top of my head is mainly that you may have to, this is something we're going to have to implement at some point, handle situations where you may allocate more or less bandwidth to the DisplayPort portion of the USB-C cable. But as for power delivery and stuff, that's pretty much all handled by the firmware, luckily, so we don't really have to be concerned with that. All right. We all good? All right. Thank you very much.